All right, welcome back to the land of the living. So our task today is to write a queue. We talked about this last time. We just wanted to write a basic linked list queue that used our linked list code. And I had said that before doing this, I was going to go fix our linked list code so it interfaces nicely. And I'm halfway through it. So we're just going to write the queue and move forward. By the time I upload it all, it will be ready to go. All right, happenings this week. I don't think there's too much. I pushed back the assignment from Wednesday to Friday because it didn't really make sense to go over a circular queue today and then make an implementation of that due tomorrow. So I don't yet know what the next assignment will look like. It is very likely that it will be due next Wednesday as normal, and I should be able to get that to you by tomorrow. So basically the reasonable same timeline that we have. So I am here to support you through that, of course. So let me know as you begin struggling with that. I'm here to help you through it. All right, so we were going to write a queue. We were in the process of working through this. What differences did we notice between implementing the queue and the stack that we'd implemented a couple class periods ago? I know we're digging back quite a ways because we're before the exam, before the study period. It was a while ago, but yeah, there.
Well, because I started a little bit of the whole when the stack in the queue.
Yeah.
And I realized that the stack is a little easier to complete.
There's a little bit less going on there,
There's
yeah.
a little bit less going on in the queue. You're doing a lot more work, in my opinion, especially based off the instructions you gave. So, it's just a little bit more because you have to with the queue, you're going in a circle. So you have to take into account, because we're doing a circular queue, not in this case, but
yeah,
you're going in a circle, so you have to account for when the queue is full.
yes.
And everything, so it's a lot more work. Now, I don't know if it's maybe a little different with just the queue, but I know that
Yeah, it looked very similar to the stack as we implement it, but yeah, there are certainly some additional considerations that we need to figure out when we implement a circular queue, and we'll talk about that as soon as we finish implementing this, so we can talk about those differences. But if the wording on thing is confusing, please do let me know. I'm happy to clarify what's going on or what I'm looking for or intending for certain wording to be. So for a queue, first thing we need to consider are what fields. And similar to a stack, there were only a couple of them. For this, we needed the underlying list. So we are going to not allow any access to anything. So this will be private. We're going to make a singly linked list. Of course, we will need to, since it's in a separate package, we'll need to import this. That is the right one. This will also need to be a queue of T to be able to make a singly linked list of T. All right, so we have the list. We're good to just make a size, and that should be everything we need. After thinking about the fields that we need, it's time to think about a constructor. So how do we initialize one of these things? Thoughts? Actually, I read back through this ever so slightly, but I think we're going to want some way to distinguish between the type. So if you ever just refactor, rename something like that, it will propagate through everything. So you'll see that the class was renamed for me. Nothing was a compilation error. So let's go ahead and write a constructor now. What do we want our constructor to do? Purpose of my constructor is to set the value of the fields. So what should the fields be? We set it to
Replace equals and we see one plus and then the size equals 0.
Perfect. For a new list, we make an empty singly linked list. And we set the size to 0. So now we have an empty queue waiting for us. Would there be an issue if we wanted to take the list as a parameter to the linked list as a constructor? Could we start with a queue of an existing linked list? That's something that we could do. If we wanted to implement that functionality, what should we do? Overload the constructor? Yeah, we could absolutely do that. Why not? Let's allow the user to do that as well. All right, that should overload the constructor to work in both of these cases.
How is that overloading the constructor? Can you like explain that when we're doing it?
Yeah. Yeah, so overload just means you have two methods of exactly the same name that differ in the parameters that they take in. So we have two different ways to call the constructor. If we call it with no parameter, we're saying we don't have a list ready for the queue, please make me a new one.
Oh, okay.
And
Other one, in case.
Yeah.
You have stuff.
if the user has a list that is already pre-populated and you say, I want this to be the underlying structure of my queue so that I can use the NQ and DQ logic that we're about to write, that allows us now to have the user call this in a couple of ways.
I'm just wondering, like, if we're making a queue link list off of a list in size 3, why are we initializing the size 0?
Yeah, you're right, size should be list.size, but that's a great question. It's Moosdale. You weren't here for the joke, it was bad. All right, other methods that we should write.
Like,
Start with the NQ,
yeah.
probably, yeah. So the NQ isn't going to return anything to us. Always have to make sure I spell that right because it's very easy and it looks a little strange. If you look at Q too long, it starts to just mess with you as a word. It'll take one parameter, what we want to enqueue, and then we want to add that to the list. So we can call the lists functions. We just say list.add. Because it's the queue and we want to add at the end, we will just do that. Especially with a singly linked list, this might become something that's reasonably important. You don't want to do anything with a find node before immediately in it. What happens if we do this? Is this a linear time operation or a constant time operation?
Constant since we have a tail reference.
Yeah, since we have a tail reference and we're adding at the end, that would be a constant time. So nowhere in this call at the end are we going to be calling with a singly linked list find node before. Remember, that's one of the things we need to make sure of when we're writing this queue. Even if we're using existing calls and they compile and they work, the purpose of a queue is to reduce the complexity of the list from a linear time operation to only allowing constant time operations. So we have to be absolutely sure of that for everything that we do. Last thing we need to think about is bumping up the size. This bumps up the size of the queue, not the size of the list. That's it. That's NQ. That's right, DQ. A DQ is going to return an element to us, so it's going to return something of type T. Not going to take any parameter. So here is somewhere where we could check for an exception and make sure that this is not an empty queue when we want to DQ. I'm going to skip that for the moment, but it is something that we might want to think about. we're going to make a node that's going to be that we use this node, access the data of this node to get it back. So we're going to make a reference that we're going to call, what do we want something? It's just for this method. We can use temp. I hate temp. We'll use temp just to show how much I loathe. We need to set it to, should start out as the head, I think. Because in the queue, we want to dequeue from the front. We need to import our singly linked node. So we want to dequeue from the front of this list, which means that we want to get rid of the head. We want to remove the head, but before we remove it, we have to store it off, store it as something. So as we do this, maybe we want some additional functionality in our list. If we call list.remove on the head, what did remove do? What does it return to us?
Here's the value.
Yeah, return to us the value that we removed. Okay. What if, is that a constant time operation? That's the next question to ask. Is removing the head of a linked list a constant time operation? Yes. So what if we just did that instead? We could immediately return remove. Would that work? Rather than storing the list, the node itself, and then trying to figure out how to change the head, we already wrote all of that logic. So let's just see if we can do this in one line. Return.
Doesn't it take an index?
So you just say return.
Yeah, remove does either take an index. So you can't pass remove a node, right? That wouldn't make sense. So if we remove at index 0 rather than all of this, does that work? Yeah, we can't just call remove, we have to call list.remove. So if we do that, list.remove should give us that first element. That element is of type T. We return that type T, matches with this type T that we said it will return. And DQ is just a new name basically for removing the head of the list. This, of course, assumes that there's an element there. So this could give you a very unfortunate null pointer exception if the list doesn't have something at index 0. Or an illegal, whatever we said, what we would throw with our remove, actually, it would give us that. But assuming that this will work, I think we are okay with our DQ.
And then would we just decrement the size of the queue before?
Yeah, we probably need to do that too, though.
Before it.
Yeah, returning, yeah, doing that after a return is going to be fun. All right, I think our DQ is done. Couple other things we want to allow the user to do. Peek, which is the same thing as DQ, but without removing it from the list. So peek should just return to us list.get at index 0, so give us the head. There, I also did implement I think a getter for everything, so I could even say get head here if I wanted to. That would work as well, but apparently I haven't implemented that. If I did do that, then I could do that. That would be fine. All right. The last thing we said is we want a size. This just follows pretty typical syntax for collections. All collections have a size, so we'll just return size. This just becomes our getter for size. You could call this get size. You could do whatever else you wanted with that, but last thing we wanted to implement was an is empty, checking whether the list is empty. Same as empty written for just about everything else. Just returning the Boolean of whether the size is 0 or not 0. This is it. This is the queue. It is done. Very simple, very easy to implement, just like our stack. But we will see that this queue has some issues. And the issues of this queue are handled by the concept of the circular queue. So I'm actually going to get into talking about that as to why that is an issue. But does everyone feel like they understand at least the basic implementation of a queue? How this works? Yeah,
I remember we talked about this a couple days ago, but, am I correct in thinking that you like switch, like where adding and where removing? So,
yes.
Like you could first and remove that last instead of adding the last and removing that first.
Yes, as long as everything would be constant time. And if you're adding at the head, then you're making a new node and attaching it and moving the head forward. There's nothing that iterates through the list when you do that. When you remove at the end, what happens? You need access to the node before the tail in order to assign that to be the next tail, and that would work if this was anything other than a singly linked list.
Okay.
But since this is a singly linked list, that would require a call to get node before the tail so that we could move the tail forward. So we ended up having to implement it this way in order for this to be constant time on everything. But if we had a doubly linked list or any other kind of linked list, then yes, you would be able to swap them. Great question. Any others before we move on to talking about what a circular queue is and why that is a better implementation than this one? All right, so whenever we use an underlying array structure as or for our queue, our linked list doesn't matter. Our implementation here is going to be just fine. But sometimes you really need to make a queue out of an array. So to do this, we will need to do some gymnastics, a little bit of mental gymnastics. So here's an example. We're going to declare an array with 5 elements, just nice and small so that we can all visualize it. We, of course, want to make it large enough to hold any data that it will eventually contain. And because we want to eventually have it contain, maybe thinking at most 5 elements, that's good enough. We do know that when we need to resize an array, that it is inefficient. It's a linear time operation to resize an array. And what's actually going on underneath the hood when you need to resize an array, you can imagine having some call, kind of like, let's say, let's make our array of 5 elements. And let's say it got full. We added 1, 2, 3, 4, and 5, and we wanted to add another element to this. So we had to resize our array. To do this, usually what happens is you make a new array that is twice the length of the old array. And then you copy over every element. For each element in the old array, copy it into place in the new array. And then you have this extra space that you can work with, including adding the element that you wanted to add, but you couldn't add here. You can see how this is a linear time operation and depends on the size of this array. The more elements are in this original array, the more work it's going to be to resize the array. Questions on that or why that's a linear time operation? There's no real magical way to do this. We need a secondary array. We can't just make additional space here because arrays are stored contiguously in memory. We don't know what's in this memory. We can't just overwrite what's in that without checking whether it's free first or not. And if it's not free, then we're still going to need to go through something that is a linear time operation to be able to make more space and copy it all over because it has to be stored contiguously. we need to resize it, we can just call a resize method. But if you call that resize method is still linear in nature, the built-in resize. So you don't have to reinvent the wheel here, you just have to know the complexity of the calls that you would make to built-in functions. So if we attach the back of the array to the front of the array, this allows us to start to be able to add and remove, keeping track of where the front and where the rear are. So let's go ahead and just do some basic work with a circular queue. So I'm going to start off with 4 elements in this circular queue, and we will do a resize if we need to. So we will start with an element there, and there. We have index 0, 1, 2, and 3 on a circular, looks like something that might try to save your life if you ever start drowning, but we're going to call this a circular array. Let's say we want to start adding and removing some things. So we're going to say that this is currently the front and the rear. So remember that we add to the rear and we remove from the front, and if they're both pointing at the same element, then it's empty. So let's start by doing some operations. We kind of have to at least start by adding, but or NQing, imagine NQing some value. I'm going to NQ the number 9. As I do this, we have to figure out where the rear, where the front and the rear are. How does that change when we do something like this operation? What should change, assuming we add at the rear and remove from the front? Yeah.
So here, the change, so like if you're thinking about it, you have start and 0, well, I call it start and end, because that's how I work, but I can use front here. So front is 0, rear is 0, so when you NQ, rear is gonna move.
Yes,
Start's
we need
gonna stay in place.
rear to move to here,
Yeah, you gotta move rear to the next spot,
because this is going to prepare us now for the next whatever it is that we're going to get to do. If we wanted to NQ, we NQ at the rear, so we're going to point the rear here to say if the next operation is an NQ, we should write that number here. If that operation is a DQ, we want the front to still point to the first element, the element that's been in the queue the longest. So it's okay that the front is still pointing at 0. That is what we would want to DQ if we wanted to. So it could be an operation, and we will do that operation. We'll see how it affects the queue. We're going to NQ again, or are we going to DQ? DQ. So to do this, we're actually not even going to get rid of this 9. We're not even going to get rid of it. We're just going to move the front. So now the front is also pointing at the 1. This tells us the queue is empty. Regardless of the fact that there is a 9 here in position 0 in our underlying array, that does not matter because these 2 values pointing at the same thing tells us the queue is empty. And also the fact that there's nothing there. But there could be something there that was an old value. So it wouldn't matter. All right, let's do a couple of NQs. What should I NQ? Give me a value. All right, we'll throw an 8 in here. And then what do we do? Bump up the rear. Oh, sounds so weird to say. All right, let's NQ again. Value. We'll just walk down the number line. 7, bump up the rear. Let's NQ again. Value. We sound thrilled this morning. Are we all just tired off of a nice long weekend? I feel that. So we'll bump up the rear again. And we can see. It looks like this is full, but it's actually not, because the rear is pointing still at this value. So. Now we can try to NQ one more time. That is a legal move. This 9 is not technically in the array, even though, or in the list, even though it's still here. But we could NQ a 5. This is a familiar situation. The front and the rear are pointing to the same location. But now when we query the size, what would the size say? Size would say it is the size of the queue, the size of the underlying list. So that's an important check we need to make. When these point to each other, either the queue is empty or the queue is full. So we have to check based on the size of the queue to figure out which of those cases it is. But let's say we wanted to NQ one more time. We want to put a 4 in here and now there's no space. We still have to do an array resize. So regardless of this, how we're going to do this is we do still have to go make a new queue. And I'm going to draw this now as, let's see. We have index 0, 1, 2, 3, 4, 5, 6, and 7 on a new circular queue now of size 8. The rest of this process is going to be starting at the front of the queue and going up to, but not including the rear of the queue. We now want to move these elements into something that starts at this element, at element 0. So we would say starting at the front. We're going to take this 8 and we're going to put it here. Then we're going to bump up the front. Take the 7. Bump up the front. Take the 6. Bump up the front. Until we have this situation. If we would bump up the front one more time and get it back to the rear, that's where we know we want to terminate. So regardless of where this value is in the queue, we knew that it was the first element of the queue because that's what front pointed to. We just take those values and starting at index 0, we add them. Now, should this be allowed? Remember that a queue has to be a constant time operation. Everything has to be constant. Is something like this actually allowed? I'll spoil it. It is. Can anyone justify it? How can this be considered a constant time operation when it is not a constant time operation? This is a linear time operation. This gets into a concept that I think you will see in algorithms, but I want to at least introduce it because this is the first time it shows up in the curriculum. If you've ever heard of the concept of amortized time or amortized analysis, that is what this concept is called. And basically, we want to look at, if we wanted to do a bunch of operations, what is the maximum number of resizes that we would need to do to fill those operations? Let's say we started with an empty circular queue of size 4. If we wanted to do 8 NQs, how many total operations would there be for those 8 NQs? One, 2, 3, 4, moving 5, 6, 7, 8, adding again 9, 10, 11, 12 total operations. 8 constant NQs and 1 linear time mapping of the size of the queue to this. But what analysis will tell us is we can't do that linear time operation every time. We can only NQ when this is full. So we will have to do an extra 4, we can do 4 total NQs before we need to do something that takes 4 total time. And then we can do up to 4 more NQs before we do something that costs 8. And then we can do 8 more NQs before we do something that costs 16. So basically, if you look at all of this, it's going to be capped by twice the number of tasks that you are doing. So if you look at this in the aggregate and just NQ, 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 and don't even worry about dequeuing any of this, the worst that it's going to be is 2 times the number of operations that you have requested, 2 times the number of NQs, which means the average NQ, even with these linear time operations happening, is 2, which is constant. So amortized time and amortized analysis basically says, how frequently can this operation be called? Is it proportional to the size of the input when we do this, or does that kind of cancel each other out? And you have a constant number of operations for the average NQ. Now you're looking not at the worst case of an NQ, that is still linear. But the average case of a bunch of NQs, you can't do this in such a way where that complexity is still linear, it must be constant. So I'm not going to dive too much into how we calculate amortized time, the different methods we have for that. There are 3 different ways that we can calculate amortized time. One of them is based on keeping track of things kind of like this. One of them is based on the concept of potential energy borrowed from physics. But you can sometimes do something that looks like it is a linear time operation, but with further analysis, you can see that over the large picture of something you are doing, it is different than its worst case behavior. Any questions on that? Again, just introducing it to you. It won't be on any exam in here. It won't be on anything, any homework showing up in any other way, but just putting that idea out there because you will eventually see it again. And now you've seen it before. All right, so that's the concept of resizing an array when it gets too full and why we allow that inside of an array-based circular queue. So you will be fully implementing this on your homework that is due on Friday. But all you really need to do is keep track of that front pointer, that rear pointer, making sure that they're filling things up correctly. If they're pointing at the same location, check the size. Is it 0 or is it full? If it's full and you're trying to NQ, then you'll need to resize the array. Any questions on that before you get started trying it for homework?
Can you post like the new slides?
Yes.
Okay, because
Yeah.
on the homework, I was like, you said slide number 6 and I was like, there's nothing.
It's not up yet. Yeah, it's because I hadn't covered it in class yet. And that's why I pushed it back to Friday. As I didn't anticipate that people were going to try to get this done over the weekend. But for those of you who I knew were trying to do that, I thought it would probably be better if you waited until after we went over it in class. But now I think people can be successful with it. Yeah.
When we resizing a circular queue, do we always make it double?
Yes, and the reason we always make it double is it allows you to do twice as much, and also it keeps things the same if you ever want to shrink the array. So if an array ever becomes less than 25% full, the idea is that you'll downsize it to be half the size. So you'll resize down rather than resize up, and that's not part of your homework, but that's how it works underneath the hood for any kind of array-based circular array. That circular queue, that gives you that same guarantee. It's still amortized constant to be able to do that, and that becomes a cost saving or a memory saving metric. If you were going to NQ a billion times and then DQ a billion times, you wouldn't still want a billion sized array. there when you have 5 elements in it. There would be no reason for that. Yeah,
So since the homework is with linked lists, and I was like, just put an array. Is
Yeah.
it still apply the same way where like, if you, I don't know, reach the last node of the linked list, you need to set size to double what it currently was?
yeah, so we don't need to do, you will need to change the size of it, so in the homework, there is the API, I pass you right to the API that tells you how to call that resize. Basically, you're just gonna give it the new size, and that will allow it to do that. So you'll just, when you pass it the current size, whatever that happens to be, times 2, and that will double the size of it and go through that linear time process. However, if you want to make sure that you're starting at the front of the linked list, that might become a little bit tricky to make sure that that resize is doing exactly what it needs to. So think about the order in which you're passing things in. Make sure that it gets put in the correct order.
When you create a brand new array list, what's the default size?
I believe that's on the API as well, but I'm almost sure it is 8.
Okay.
Unless it has changed in recent Java versions. I haven't checked in a while, but at least it used to be 8 the last time I checked. Other questions about circular queues before we head on to our next big topic? All right, so we have gone through. We've gone through our first big set of data structures. We've gone through all of our list-based data structures, including our restricted list-based data structures, our stacks and our queues, which restrict the functionality of a list to improve on the time it takes to run. So we're going to start looking at some new data structures for some new concepts, or some, maybe not some new concepts, but for some concepts that we've seen before that we want to be able to put into code. So the first would be the mathematical set. Who is either taking discrete or has taken discrete before? We all know what a set is. We've seen a mathematical set or know that concept. So they're cool, right? I guess. You can imagine wanting to actually have a programmatic structure that represents a mathematical set. What's the difference between a math set and a list that we have that we could use? Something like an array list or a linked list. What's the differences in functionality? Yeah, yeah, sets don't really have positions, right? They're either members or they are not. So we have the concept of membership. We don't really have a concept of placement within the set. So that's the first big change. Yeah.
Uniqueness in sets?
There is uniqueness in sets as well. If you have duplication, it's equivalent to not having duplication. We either care about, yeah, something is in the set or not. There is no, the concept of number of elements, number of unique elements is there, but the number of a particular element is not. So order does not matter and multiplicity does not matter. Those are the two big concepts in a set. So how are we going to emulate this concept? Do we want to use an underlying list for this? Thinking about this, you absolutely could. How would you do it? So you still want to do everything that you could do with a list, add, remove, etc. But now we want some additional logic that says this is a math set.
Would you want like, parentheses, like, you know, a range?
Yeah, we'd need some way of saying something like, all right, when I want to add something, I can't just go add it. Now I have to check and see if there are other elements of that same value. If there's another of that same value, then I don't want to add it to the list. If it's already there, I don't want to, but if it's not, then I do. So now adding anywhere becomes a linear time operation. We have to check and make sure for that multiplicity. On the other hand, we could just say we're going to allow duplicates. But if you allow duplicates, whenever I want to query the size of the set, now I have to go through and figure out the number of unique elements, whether there are duplicates, how many duplicates. That becomes much more difficult. So we're going through this process of making whether does it make sense to use a list to model a set. Talking about efficiency, we find that it seems like the list actually gets less efficient rather than more efficient. So it would be nice if we could find a way to model this concept of a math set in ways that are faster than a list would be able to handle that. So if we build in some additional functionality into a list, maybe we could answer some of these questions in less time. So let's first take a look at the set abstract data type. So what does a set actually contain before we dive into what is the underlying structure for a set going to be? So the functionality that we want from a set, we want to be able to add, just like we did from a list, and figure out whether that add successful or not. Now that becomes pretty important in a set. If we try to add an element, it can return us, yes, we added it to the set, or no, it was already in the set, so we didn't add it, which is why we want to return a Boolean that would tell us that information just from returning from attempting to add to the set. We could also do an add all. So we're going to take in any other collection type. This could be a list, this could be a stack, this could be any other collection. And we want to add every element from that collection into our set. Of course, ignoring order and multiplicity. So if a list has multiple elements, we would only add it to our set once. Of course, if we add, remember that our add handles that. So we'll return true from this add all if at least one element was added. We want to be able to clear our set, removing all of the elements. We want to be able to determine whether our set contains a query, whether it contains everything in a collection. So true if the set contains every element from this collection that's being passed in as a parameter. Equals tells us whether this other object is a set that contains exactly the same elements as the set that is this current object. We want to be able to do set operations on sets. So let's say we want to pass in another set, and then we want to take the set difference between these two sets. So we'll say that this set minus the other set, and this gives us the new this set. Or rather, we're gonna pass that back as a return value. So returns a new object that is the difference between this set and the parameter set. So this set minus that set. Give people just a minute to jot down whatever notes they want to on this, because there's another page. This is in alphabetical order. Lots of things you want to be able to do to sets. Next, we want to be able to take the intersection between two sets. So we will, just like before, pass in another set as a parameter and return a new set that is the intersect of this set that is this object and the other set that's passed in as a parameter. We can figure out if this set is empty. We want to be able to remove elements from sets. So we pass in an item we want to remove, and the return tells us whether we successfully removed it, whether it was present or not. If it was not present, then we would return false. If it was present, then we would remove it and then return true. We can do the exact same thing with a whole collection, removing every element from that collection, from this set. There's a similar to remove called retain. Retain all says that we're going to remove everything that isn't in this collection. So it's kind of the opposite of remove all. So we're going to remove everything other than what is in this collection. We have a size, number of elements in the set, which is known as its cardinality. We'll also implement a to-array method that converts this set to a list object and returns that. This could either be directly an array, you could say that this is an array list, whatever. I just put this as a basic array. So an array containing the elements of the set in case you wanted to convert the set to a list. We still need to be able to union, so we'll take another set and add all elements from that set into this set and returning a new set rather than adding them to this set. So this just returns a new set with the union. So it's very much like an add all. In fact, you could implement this with add all after you made the new list. So if you made a deep copy of this set and then said add all from that, that's what you want to return. So you can make that a nice couple of lines. We're not actually going to implement this in class, but this is in general what you can expect from a set. And do know that there is a built-in set in Java. So if you're ever trying to use a math set, don't code it yourself. You can just import it and use it. But now we want to justify how can sets actually be implemented? In fact, there are two main implementations of a set that use two different data structures for storing them. The first is a hash set, and the hash set uses an underlying hash table. And the second one is a tree set using an underlying binary search tree. And we'll talk about binary search trees later, but I wanted to talk about sets as the way to tie us to why are we studying hash tables? Why are we studying trees? Well, trees have a ton of uses, as do hash tables. But we'll start by justifying it as you can use them to represent a mathematical set. Let's take a look at what would happen if we wanted to implement this with an array. All of these operations that we just talked about, which ones feel unnecessarily slow? We talked about add being slow because now we have to search the entire underlying array to figure out, does this set contain this element? We don't want to add it if it does, because we don't care about multiplicity. Rather than doing this, we could assume, okay, well, rather than storing things all willy-nilly in our array, what if we sorted them? And we said, at all points in time, this array is sorted. If that were the case, then we could figure out whether something was in the array much faster, because instead of searching the entire array, we could use binary search. We talked about how binary search is logarithmic in complexity compared to the linear time regular search through everything. But if we did that, then we would have to create, it still creates a linear time insertion, because we would still, once we found where it goes, would have to make space for it. And assuming that on average, it's somewhere in the middle, that would be still a linear time procedure. So even if we tried to make this process faster, there's still a limiting constraint that doesn't allow us to do that. Remove is also linear. Again, we have to find where it is in the array. Assuming that there's only one of it, we would still have to figure out where it is. We could, again, use binary search, but then we would have to resort the list afterwards. Oh, sorry, it must be sorted anyway. So whenever you would add something, you have to add it to the right place. If you do all of that, then remove could be logarithmic. But this logic extends to just about every other operation in this. It is unfortunately not efficient enough because we want to be able to add and remove faster than linear time. This linear time add and remove gets really bad when you need to be doing this all the time. So, two solutions to this. They use structures that we haven't seen before. And we are going to come back tomorrow and figure out exactly what those are. At least we'll start with the hash table and get a lot of experience with it. It's the most complicated structure you've seen so far, probably. which means that it'll be nice and fun. Talk about it.
You're gonna do so good.
The kind of, some of the engineering.
So yes and no. So the dictionary in Python is a map in Java. And a map involves, so it's a set linked to a linked list. So every element of that set has a linked list that's associated with it. And so it can use a hash table, but it's a hash table, where every element of that hash table is itself.
I'm saying a lot.
Yeah. Would be a dictionary.
Oh,